Let's recall that in the previous video on differential equations, we defined an exact differential equation. And we also saw how difficult it is to simply use the definition to decide if a given equation is exact or not. So to help us with that, we today have this theorem. So let's see the statement. We again have our differential equation in the differential form m dx plus n dy is equal to 0, where we know that m and n are, each one of them is a function of two variables x and y. But now we are going to put some extra conditions on m and n, namely that they have continuous first partial derivatives at all points x comma y in some rectangular domain D. So the domain D on which we are considering these functions m and n is a rectangular domain. Okay, it is still a domain, it is still open and connected, but it's rectangular in shape. And what are these conditions? These conditions say that for both m and n, the two partial derivatives, one with respect to x and the other one with respect to y, are both continuous in this domain. So they both exist, of course, also. Then, if the differential equation is exact, which means that if the left hand side expression is an exact differential, then the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x throughout D, for all x comma y belonging to D. And conversely, if this condition is true, then the differential equation is exact in D. Now let's prove this. So this is the proof. The proof, of course, has two parts. In part 1, we assume that the equation is exact. Then, of course, we know what that means. That means that there exists a function f from the domain into the set of real numbers, which has continuous first partial derivatives, just like m and n, such that the total differential of this function f equals that expression m dx plus n dy, or in other words, the first derivative of f with respect to x, partial derivative, is m, and the derivative of f with respect to y is n. In D means you can write x comma y here and x comma y here with m as well. Then this equality is true for all x comma y belonging to D. Instead of writing all those things, I have simply written in short like this. Okay. Now you can differentiate this, both sides of this first equation again, partially with respect to y. What allows you to do so? Recall that it was given that m itself has two first partial derivatives which not only exist but are continuous also. In particular, m can be differentiated partially with respect to y. So that allows us to differentiate both sides with respect to y, which gives this second partial derivative of f with respect to x first and then y on this side, and on this side you have del m del y. Similarly, you can differentiate both sides of the second equation partially with respect to x. That gives you this del square f del x del y. Note that here we have del x del y, here we have del y del x, and the right hand side is del n del x. In D means again that these equations are true for all x comma y belonging to D. Now, since m and n have continuous first partial derivatives, in fact this is the condition on m and n. So obviously f has continuous second partial derivatives, because already the first partial derivatives of f with respect to x and y are m and n. So if m and n themselves have partial derivatives which are continuous, so f can be differentiated partially 2 times, and those second derivatives would also be continuous. then let's see. Actually, then a result from calculus says that these two second derivatives are equal in spite of this different order. So that means these two will be equal. So let's write those things. So the result I was talking about has this name, Clairaut's theorem. You can find it as theorem 1754 in Terence Tau's analysis 2. Okay, we haven't really got to this part. It is still somewhat far away from us, although we have started analysis 2. But anyway, you can find this in any calculus book also, which treats multivariable calculus. So because of that, these two derivatives are equal, second derivatives of f, mixed derivatives. And that is why these two are also equal, and that's what we have to show. That is part 1. Now next, let's prove part 2. So in part 2, of course, we start with this condition, which is what we proved in part 1 because it is the converse. So del m del y is equal to del n del x in D. And now we want to prove that our equation is exact, which just means that we want to show that there exists a function f like that, which has first continuous partial derivatives and for which these equations are true. Del f del x equals m and del f del y equals n in D. That in D thing is there in the background, okay, do not forget it. Now, it's not a very difficult task to find an f that satisfies the first equation or an f that satisfies the second equation, but we want an f that satisfies both the equations. If you ask me how it is easy to find an f say which satisfies the first equation, well, the answer is you integrate. The derivative of f with respect to x is n. You don't know f, you know n. So you integrate both sides with respect to x. But you may say, but f is a function of x and y. Well, you keep y constant, that's it. You treat y as a constant in the sense that for all y for which some x comma y belongs to D have to be considered but one y at a time. When you choose one value of y, then y stays constant and x changes, or rather I should say like this, y stays constant, that is this thing stays constant and x changes. So that way you will get an f, and that way you will also get an f from this second equation. But how can we combine these two things? Let's see. Okay, so we want to find f, and let us suppose for the time being that f exists, and then we try to see what f can possibly be. What is the consequence of f's existence? Now, if you apply that thing to this equation that I said just now, that integrate both sides with respect to x, you are going to get this. The left hand side, of course, would be f, and the right hand side is you integrate m with respect to x. You see del x here, the author used this del x to really emphasize the fact that the integration is with respect to x and y is kept constant. But you can write dx here if you want. Okay, nothing will change. Plus phi of y, where phi is an arbitrary function of y only. Why? Why should you add an extra phi of y? Well, you cannot just simply carelessly say integrate both sides with respect to x and that will give you this. You should know why each object that you see here is there and does it really exist? What is this thing? Whenever you are integrating like that, you are actually writing an antiderivative. What is an antiderivative? An antiderivative is, in other words, indefinite integral. Say the derivative of sin x with respect to x is cos x. So, an antiderivative of cos x with respect to x is sin x. Did you notice what I said? The derivative of sin x with respect to x is cos x, but an antiderivative of cos x with respect to x is sin x. There are multiple antiderivatives, and you already know that this fact is expressed by writing a plus c on this side whenever you do indefinite integration, so that if you do the opposite thing to this side, that is, if you differentiate it back, any such function should give you that thing, the original thing. Now, if you think of this process of integrating both sides with respect to x, in this entire process y is constant. So, if you add a function of y only on this side and then you think of doing the opposite to get that equation back, obviously you are going to do what? Differentiate both sides partially with respect to x. That will contribute, this term then will contribute 0, whereas this will give you m. That means the integral that you are looking at here is an antiderivative of m with respect to x. But does it exist? Unfortunately, antiderivatives don't always exist. However, in this case, it exists. Let's see how. The first fundamental theorem of calculus ensures that we have this. Well, the first fundamental theorem of calculus tells us that if we have a continuous Riemann integrable function, then that type of functions, such functions have antiderivatives. Is our function m continuous? Yes, m is continuous, because it's given that m has partial derivatives which themselves are continuous. So, obviously, m is also continuous. In fact, we don't really need the entire continuity of m here, but we only need m to be continuous as a function of x, because that's the variable with respect to which everything is going on here. Yes, that is also true. And if you really want to see what is going on geometrically, because we are talking about these things in a rectangular domain, then this is the explanation. Okay, let me draw a small figure. Say this is your rectangular domain. This is your D. Although it's not given that the sides of the rectangle have to be parallel to the coordinate axis, but I know that that is what the author wanted to mean when he wrote rectangular domain. So, as a domain, it is still connected you can of course see, and open, which means that these boundary points are not there, it's the interior of that rectangular region. So, what we are looking at here is happening for any chosen value of y. So, if you fix y and then concentrate on x, you then have a line like this, whose ends of course are not there, because we are talking about the interior of this rectangular region. That is a fixed y. In this fixed y, wherever you concentrate your process, that is your thing, you can consider a closed interval. In that closed interval, as a function of x, m is continuous, and whenever you have a continuous function in a closed interval, it is automatically remain integrable, and that is why this integral exists. Okay, that is why this integral exists, and additionally, because the function is continuous, there is an antiderivative. But we are of course not considering definite integral, but in this case antiderivative exists. Okay, it comes from single variable calculus. Okay, so that's the thing. That is why this exists, and if you add an arbitrary function, in case of a single variable function, you add an arbitrary constant. In this case, there is one variable which is being held constant. So that is why in this case you add an arbitrary function of that. Okay, so if f exists, then this has to happen. Now let's see now where we can go with this. You obviously understand that this thing has come from this one only. Now we have to somehow involve this one. So we would differentiate both sides with respect to y, and that's what we are going to do. Okay, so we do that. We use the fact that n should also be equal to del f del y, and from here we find that del f del y is del y of this integral plus del y of this function phi, but because phi is a function of y only, so partial derivative turns into ordinary derivative. Now what we do, we keep this on one side and transfer this on the other side. So you get n minus that thing. In d is of course always there. Now because phi is a function of y only, if you differentiate phi with respect to y, that will again be a function of y only. There is no x, it doesn't depend on x. So this side is independent of x. So obviously the right hand side, that is this, should also be independent of x. And with this information, now if you differentiate this partially with respect to x, because there is no x, you should get 0. Okay, so that's the next observation. So we should have this, that is, if you differentiate this partially with respect to x, you should get 0. Up to this stage, we have been working with the assumption that such an f exists. Remember that. Okay, we haven't really found f or shown that f exists. In fact, that is our aim in this part too. But we have come to know after working this much that if f exists, then this should be true. Now we are going to propose one f, and our f will just be that is f is integral of m with respect to x plus phi of y, where phi is any function of y. Will any function of y really give us these things? Yes, actually that's the case. So that is the next thing. Let's see how. Okay, so we start from this another paragraph. Actually, the second part, you can say, really starts from here. So the proposed function f is this, and you already know by now why this exists, why we are putting f phi of y here, although it is just simply, at this stage, it is just some proposed function. At least we know that these things, there is no problem with them. And where phi is some function of y only, does not really matter what function, any function of y. Now with this, this part may seem like repetition, but again, keep in mind that whatever we did before this, that was only for us to see what happens if f exists. Now we have chosen a candidate for this function, And now we want to show that for this chosen f, really those things are true. So we again differentiate f with respect to y, that of course gives us that. But then what we do, here we again differentiate this partially with respect to x. That will make this side this. And what will happen to this expression if we differentiate this partially with respect to x? The first term will turn into this, because already there is a partial derivative with respect to y, and then again you are differentiating partially with respect to x. So this is, this is okay. But this is again a function of y only, so differentiating it partially with respect to x gives you 0. So after this there is nothing. And now we take this thing back, okay, here. So if you just simply apply the partial derivative on n and on this, so you are going to get this. Now in place of this term, you can use that one. So that's how the calculation next is going to progress. Let's see. Okay, so we use this fact, that is, this is equal to this here, and then it becomes this. Now again you can use Clairaut's theorem, because f is twice continuously differentiable, the second order partial derivatives of f exist and they are continuous. So you can change del x del y to del y del x, and then this thing is equal to this. Why? Because our original f was this. So if you differentiate both sides partially with respect to x, this is antiderivative with respect to x, so differentiating this will give you m back, and this of course contributes 0. So m equals del f del x, but this is the del y of del f del x, so this is del m del y. And now finally you use the hypothesis of part 2 that these two things are equal, so that way you get 0. So yes, your chosen f really works. It satisfies both the conditions. That means it is the function that we were seeking. But still there is some part left, so let's do that next. Okay, so any such function phi works. And if we go back to the equation which has the phi, that is this differential equation, d phi dy equals this thing, then from that you can get phi by integrating. Now you may think why I am not putting a constant plus p here. Well, any such phi works, and so we can give one f which comes for that phi. And then when we go to the issue of actually integrating the differential equation or solving it, there a constant will appear. Okay, so it's not that by not writing a constant here plus c we are losing anything. No. So this is just one antiderivative of phi. One function whose derivative is this. So this is one phi. Now you can take this partial derivative with respect to y inside this integral and differentiate m first, because the integration is with respect to x. So integration with respect to x and differentiation with respect to y, these things are independent. That is why. And now if you use this phi back to this expression for f, then it will look next like this. Like this. And this f set is going to satisfy both these conditions. And that is why, because of the existence of one such f, our differential equation is exact in the domain D. Now there are some examples that come next which will illustrate this thing. Oh, and one more thing, when we eventually solve this differential equation, in that solution this f will appear. In fact, that solution will be f equal to some arbitrary constant. But does that mean that we should remember this form so that whenever we are given this, we will do all these things and straight away write what f is and hence the solution? No, there is no need to remember this form. We will actually each time go through this process of proof. It sounds very daunting, but you will get used to it and you will see that it's not going to be long also. It will actually be very short. But let me just end the video here itself, and tomorrow we have something and I forgot. So we will see what it is tomorrow. Until then, this is me, Lucifer from a mathematical group. Have a nice day.